Hi everyone. So in the last part we talk about the forms of Q and K, right? So Q is the reaction quotient and K is the equilibrium constant. Now depending on the Q and the K, we can see which direction a reaction should proceed in order to reach the equilibrium. Okay, so the value of the Q, which is the ratio of products to reactants, which indicates the direction in which a reaction must proceed to reach equilibrium. Okay, so the value of Q tells us the ratio of the products to reactants at any given time. It doesn't have to be necessarily at the equilibrium. Okay, if Q, which is a reaction quotient, less than K, okay, meaning, so how do we calculate Q? Q basically concentration of products over reactants, right? Q. So if Q less than K, meaning the denominator, your reactants, is large relative to the numerator, products, right? So for Q to equal K, so then the reactants must decrease and the products should increase. So the reaction then proceeds towards the products, making more of the products so we can have a greater Q value. So the reaction is not at equilibrium and will progress to the right towards products until Q equals K. So the reaction will proceed making more of the products, reactants to products, until equilibrium is reached. Okay. Similarly, if Q greater than K, meaning the numerator is big, right, and you are dividing by a smaller number. So what need to be done is the numerator represent products should decrease and the denominator reactants should increase if it needs to reach the equilibrium. So how can we make the denominator or the reactants increase? By going from products to reactants, by reversing the reaction, right? So the reactants must increase and the products decrease. So the reaction proceed towards the reactants. So this would be the overall reaction. So the products will used up to make more of the reactants until equilibrium is reached. So by looking at if Q less than K or Q greater than K, we can see which direction a reaction should proceed in order for it to reach the equilibrium. Okay, if Q and the K are the same, we say the system is at equilibrium and no further net change takes place. And we can also see this in this diagram, reaction direction and the relative sizes of K and Q. Now in this one, QC is less than KC. So the reaction will proceed to making more of the products. So then as it forms more of the products, QC and KC will become equal, no net change. Let's say you have a condition where reactant QC is greater than KC. QC is greater than KC. So then the products will turn to reactants. So the reverse reaction will take place until it reaches the equilibrium where QC and KC become equal. Okay. Okay, so let's look at some of the questions that will help you to understand these concepts. For the reaction N2O4 going to NO2, reversible reaction, Kc is given as 0.21. At a point during the reaction, N2O4 equals 0.12 molarity and NO2 0.55. Is the reaction at equilibrium? If not, in which direction is it progressing? So we are given Kc and we are given at a point during the reaction, concentration of the reactants and the products are given. So from these two concentrations we can find out the QC, and if the QC is equal to KC, then it is at equilibrium. If QC less than KC, so then it has to make more products. If the QC greater than KC, so then the reverse reaction should take place. So now first thing is we need to write the expression for QC. Okay, so QC is going to be concentration of products, which is NO2 raised to the power 2 over N2O4 concentration at the given point. So NO2 0.55 and N2O2 0.12. Now do this calculation and tell me what number you would get. Take your calculator and go ahead and do it. What is that number? Is it going to be greater than Kc? Kc is given to us as 0.21. What would you get? So you should be getting a number 2.5. So Qc is 2.5 and then the Kc equals 0.21. Which is more, 0.21 or 2.5? So 2.5 is a bigger number. So QC is greater than KC. So which direction do you think reaction should proceed to become equilibrium? Since QC is greater than KC, so then the reverse reaction should take place, right? So this is your reactants and this is your products. So we want to lower this value. How do you lower it? By dividing a bigger number in the denominator. How do you make it bigger? By making more of the reactants. So the reverse reaction will take place until it reaches the equilibrium. Okay, so this is what we did. QC greater than KC, therefore the reaction is not at equilibrium and will proceed from right to left, from products to reactants until QC equals KC. Okay. Solving equilibrium problems. Now, if equilibrium quantities are given, we simply substitute these into the expression for Kc to calculate its values. Okay, if the equilibrium quantities are given. If only some equilibrium quantities are given, we use a reaction table to calculate them and find Kc. So what do we have in a reaction table? So we need to have the balanced equation. So the first thing is we always have a balanced equation. And then we're gonna find out the initial quantities of reactants and products. What's the initial amounts? And then the changes in these quantities during the reaction and the equilibrium quantities. Now we call this as ICE table. You see ICE. Initial quantities, change in these quantities during the reaction, and then the equilibrium quantities. So we're going to always construct the ICE table if we want to find out the equilibrium quantities. Okay, like this, using a reaction table to find equilibrium quantities. In a study of carbon oxidation, so carbon oxidation with carbon dioxide, evacuated vessel containing a small amount of powdered graphite, which is carbon, heated to 1080 Kelvin, gaseous carbon dioxide is added to a pressure of 0.458 atm and carbon monoxide forms. So carbon monoxide is a product, carbon dioxide and carbon is the reactants. At equilibrium, the total pressure is 0.757 atmosphere and we need to calculate the Kp. Remember we talk about the Kc and the Kp. Kp involved if it is gaseous reactants and products, and we can express the equilibrium constant in terms of pressure. Okay, so we are going to construct a ICE table. So this is the reaction. Your reactants carbon dioxide plus carbon graphite giving you 2 carbon monoxide. That's the balanced equation. So initially, so we're going to put these in terms of pressure. Initially we have carbon dioxide 0.458. Carbon doesn't matter because carbon is graphite and it is a solid. So we don't care about its quantities. Remember, for the expression for equilibrium constant, we do not put solids and liquids. Okay. And at the beginning, you have carbon dioxide, so nothing has formed. So the amount of carbon monoxide would be 0. So if 1 mole of carbon dioxide react, how many moles of carbon monoxide form? 2 moles. 1 mole of carbon dioxide react means whatever the amount that you started with, you are going to use it up, 1 mole. So similarly, X amount of carbon dioxide is going to use up, 2x amount of carbon monoxide would be formed. Since we don't know the change, we always express the change in terms of X. Meaning if the X amount, and that is going to be also the stoichiometric ratio, like 1 to 2. So X amount of carbon dioxide going to be the change. So 2 times X of carbon dioxide would be formed, plus 2x. That's the change. Now when this amount has been reacted, how much is left at the equilibrium? How much carbon dioxide left? So to begin with, you have 0.458 and X amount has been reacted. So what is left is at the equilibrium 0.458 minus X. Initial minus the change. Okay. And then the carbon monoxide amount that is being formed also going to be the same amount as the change, 2x. Okay. The amount of carbon dioxide will decrease and then the amount of carbon monoxide will increase. If we let the change in carbon dioxide equal negative x, then the change in carbon monoxide will be positive 2x. Okay. And then the equilibrium amounts are calculated by adding the change to the initial amount. Adding the change to the initial amount. Change is negative x, initial 0.458. So you add these two together. Okay. Now what we want to find out is the Kp. Now when you write down the Kp expression, remember how do you write the Kp expression for this reaction? It would be products carbon monoxide pressure, right? Carbon monoxide. Pressure carbon monoxide, and then it need to raise to the power 2 P2 carbon monoxide over pressure carbon dioxide. Are we going to put carbon? No, because it's a solid. You don't put that for your Qp. Since we don't know whether it is equilibrium or not, we can start with Qp. Okay, and then later can change it to Kp. Okay, Qp. Qp would, this is how the expression going to be. Okay, now also we are given here at equilibrium the total pressure is 0.757. How do you get the total pressure at the equilibrium? Which gases are responsible? It's a carbon dioxide and carbon monoxide. So at the equilibrium, what we have is 0.458 minus X amount of carbon dioxide plus 2x amount of carbon monoxide. So when you add these two together, since we are expressing them in terms of partial pressure, that should equal to 0.757. Okay. All right. Once we have the equilibrium amounts expressed in terms of x, we use the other information given in the problem to solve for x. So the total pressure at equilibrium given to us as 0.757, which is the combination of partial pressure of carbon dioxide and the partial pressure of carbon monoxide. Carbon dioxide, we figured out it's 0.458 minus x, carbon monoxide 2x. So when you add these two together, here you have a minus x plus 2x. This would result giving you a plus x. right? 2x minus x is x, meaning 0.458 plus x equals 0.757. So we can find out what is the x going to be. So then the x would be 0.757 minus 0.458, 0.299 atm, right? So we found what is x. Now to find the Kp, we need to find out the carbon dioxide partial pressure. That's going to be 0.458 minus the x amount. Here carbon monoxide would be 2 times the x amount we just found. So at equilibrium, pressure carbon dioxide 0.458 minus x. 458 minus x is 0.299 equals 0.159. Carbon monoxide would be 2 times x. 2 times 0.299, which is 0.598. Now we can find out the Qp. P, partial pressure of carbon monoxide raised to the power 2, 0.598 raised to the power 2 over 0.159, which is carbon dioxide. So that will give you Kp of this system. Okay. That's an example how we can use reaction table to find K. The next one, another question. Calculating Kc from concentration data. Now the previous one was based on pressure data. Now this one is for concentration. In order to study hydrogen halide decomposition, a researcher fills an evacuated 2-liter flask with 0.2 moles of hydrogen iodide gas and allows the reaction to proceed at 453 degrees Celsius. At equilibrium, Hi is given as 0.078 molar. We want to calculate the Kc. Now, how do you find the Kc? Remember, the Kc is going to be, now our products are hydrogen, H2, equilibrium concentration of hydrogen, and equilibrium concentration of iodine over equilibrium concentration of Hi. We know the equilibrium concentration of Hi. Okay. And we need to find out hydrogen and iodine. It says evacuated 2-liter flask with 0.2 moles of hydrogen iodide gas. Now from this 2 liters and 0.2 moles, we can find out the initial amount of hydrogen iodide, right? So it need to be in concentration terms. So how do you find out the concentration? You are given the volume and you are also given the number of moles. So how do you find the initial concentration of Hi then? Hi initial would be number of moles, 0.2 moles. You're going to divide it by the volume, which is 2 liters. Moles per liters, and that would give you molarity of Hi. That's the Hi initial. So we know the initial concentration of Hi. We know the equilibrium concentration of Hi2. Right? So from that we can find out hydrogen and then the equilibrium concentrations of hydrogen and iodine. So let's see how to proceed. Okay. This is how I showed you. Calculate the initial hydrogen iodide, 0.2 over 2, 0.1 molar. And then you construct the ice table, 2Hi giving you hydrogen and iodine. So initially we have 0.1 moles which we calculated here. And then the initial amount of hydrogen and iodide is 0 because no product has been formed yet. And then the change, since it's 2 hydrogen iodide, 1 Hi, 1 iodine. So the change now going to be negative 2x. Right? We don't know the x amount, but we know 2 times x since we have 2 molar ratio minus 2x. Hydrogen, since it's 1 plus x, and iodine also would be plus x amount. So at the equilibrium, what is left is, since x amount has been reacted, when you add these two together, 0.1 minus x would be the amount at the equilibrium. Okay, and then the hydrogen and iodine doesn't change from the change, it remains the same because that's the amount that has been produced at the equilibrium. And we were given the equilibrium concentration of HI as 0.078. So this is the same as this amount, 0.1 minus 2x, right? So 0.078, 0.1 minus 2x. So the 2x would be then 0.1 minus 0.078 and you divide it by 2. So you can find out the x by solving this part over here. X is 0.011, right? Meaning equilibrium concentration of hydrogen is also 0.011. Equilibrium concentration of iodine, X, also 0.011. So your Kc or the Qc would be equilibrium concentration of hydrogen times iodine over hydrogen iodide raised to the power 2. So we found X 0.011 times 0.011 over 0.078, which is the equilibrium concentration of hydrogen iodide raised to the power 2. Okay, that give you Kc value. That's another way that you can solve Kc from given data. Okay, another question. In a study of the conversion of methane to other fuels, a chemical engineer mixes gaseous CH4 and water. Now when you are reading the question, you need to identify what is going to be our reactants. CH4 gaseous plus water. In a 0.32 liter flask, volume of the flask is given at 1200 Kelvin. At equilibrium, the flask contains 0.028 moles of carbon monoxide. 0.028 moles of carbon monoxide, 0.084 moles of hydrogen. Now, we know the size of the flask, 0.32. We were given the number of moles. So, since we know the moles and the volume, from that information we can find out what's the equilibrium concentration of carbon monoxide and hydrogen. Okay, as well as methane and 0.045 moles of methane. But methane is one of our reactants. So we can find out the initial amount of methane and also, we were given the equilibrium concentration of methane. We can find out the equilibrium concentration since the equilibrium number of moles of methane given. What is the concentration at equilibrium? What is the water concentration at equilibrium? Okay, and Kc is given for this process. So methane plus water give you carbon monoxide and hydrogen gas. Okay, so to find out the concentrations of methane, equilibrium concentration of methane, going to be number of moles 0.045 over the volume 0.32, and then carbon monoxide concentration would be 0.084 over 0.32. Okay, and then equilibrium, the flask contain 0.028. 0.028, this one would be 0.028 over 0.32 carbon monoxide, and methane would be 0.045 over 0.32, and then the hydrogen would be 0.084 over 0.32, right? So when you solve these three things, you can find out the equilibrium concentrations of hydrogen, methane and carbon monoxide. Okay, over here. So we wrote the balance. So we have to first do the balanced equation, methane plus water, giving you carbon monoxide and 3 hydrogen gases, right? So here, something I forgot to do was balance it. But to find the concentrations, it's okay. But for us to write the QC or the KC expression, we want to make sure that the reaction is balanced. So here is the balanced equation. Methane plus water giving you carbon monoxide and 3 hydrogen gases. Okay. And then the QC expression would be carbon monoxide, hydrogen raised to the power 3, methane and water. Okay, now determine the equilibrium concentration. So I showed you how to find the methane, CH4 0.045 over 0.32. So likewise you can find out equilibrium concentrations for carbon monoxide and also hydrogen, which I have shown you here how to do that. Okay, and we are also given the Kc for this reaction. Remember, Kc was given to us as 0.26. So if you write the expression for the Qc or the Kc, because we are at equilibrium, so you're going to put it together: carbon monoxide, hydrogen raised to the power 3, methane and water. What we want to find out is the equilibrium concentration of water. So we can keep the water in this side and take the Kc to this side. Okay, so this can be either Kc or Qc. Okay, since we are talking about concentrations at the equilibrium. Okay, so then the water would be, we know the concentrations of carbon monoxide, hydrogen, methane and Kc was given as 0.26. So when you solve this part, we can find out the concentration of water. Okay, so we have more questions to do, but I will do the other questions in the next video. Okay, so bye for now.